All right, welcome to Chapter 5. This is Part 1, and we're going to be talking about thermochemistry. So almost all sources of energy are results of chemical reactions. Okay, we have the combustion of gasoline, we have the production of electricity from coal, and we have many others. That energy is then distributed and consumed, right? And the chemical reactions that produce energy are responsible for sustaining these different living systems. So as living organisms, we know that we consume different types of energy, right? Different forms. We take in carbohydrates, proteins, lipids from the different foods we eat. And then these molecules are broken down to produce energy for us to carry out a series of chemical reactions, which are called the catabolic pathways. And then we have the anabolic pathways, which are going to basically use this energy to perform work. Now, I'm not so interested in you memorizing this or knowing this, but I just want you to understand why energy and the study of energy is so important. Well, Chapter 5 is all about thermochemistry, and so in this chapter we're going to study energy and its changes. So in particular, we're focused on one topic called thermochemistry, which is really the study of the relationship between chemical reactions and energy changes that involve heat. So energy, can't be seen. Matter can be seen. So we define energy as the capacity to do work or to transfer heat. And so work is just the energy used to cause an object to move against the force, while heat is the energy used to cause the temperature of an object to increase. And when we talk about energy, we're really talking, the unit for this is joules, okay? And we abbreviate that with a J. It's the SI base unit, and one of the things that you should remember is that 1 calorie is equal to 4.184 joules, okay? That's a very important conversion for you to remember. It will come up on an exam. Well, there are different forms of energy, okay? First, we can look at what's called kinetic energy, which is just the energy of motion, okay? And we can define kinetic energy by E little k is equal to 1/2 mv squared, okay? And so when we talk about different atoms or particles, these are in motion, right? Atoms and particles are moving around, they have a mass, thus they must have a kinetic energy. Potential energy is a different form of energy. It's stored energy that can be converted into kinetic energy. So the easiest way of thinking about that is basically a biker that's going to be cruising down a hill. At the top of the hill, there's a high potential energy. It's a bunch of energy that's about to be released, okay? But there's zero kinetic energy. Nothing's moving. But as that biker ascends down the hill or descends down the hill, you start to decrease the potential energy and you're increasing the amount of kinetic energy. Well, two other types of energy are thermal energy and chemical energy. Okay, we're going to discuss these more in detail as we go through this chapter, but thermal energy is just the kinetic energy of atoms which are moving around. Okay, and we can measure that using temperature. Whereas chemical energy is the potential energy stored within the arrangement of atoms in a compound. Okay, so in between these different bonds between different atoms, you have energy that's being stored as potential energy. Well, when we talk about energy, we really have to define two things called the system and the surroundings, okay, which are just two parts of the universe that we can use to focus on in order to track energy changes. Well, the system includes just the molecules we want to study. And basically the system can either be open, which allows for the matter and energy to be exchanged with the surroundings. It can be closed so that only energy is exchanged with the surroundings. Or they can be isolated so that no energy or matter is exchanged with the surroundings. Okay? The surroundings is just everything else. Okay? So if you look here, just the molecules in here that are interacting is the system. It's hydrogen gas and oxygen gas. Everything else is the surroundings. Okay? So keep that in mind when we talk about the system and the surroundings. The system is only what we're really focused on. Well, we said energy can really be transferred in or out of this system. Okay? And that can be done by either causing an object to move against a force or causing a temperature change, right? And if we remember what we defined energy as, it's the capacity to do work or transfer heat. Well, we can define work as just the force multiplied by the distance. So if we have to lift an object against the force of gravity, we perform work. If the object is a system, then we are the surroundings, and thus we are performing work on the system and transferring energy to it. Okay, like a baseball player who's throwing a baseball There's a force being applied, there's distance, and so that is our work. Well, a combustion reaction is the type of reaction that we talked about back in chapter 3 and 4, which is going to release chemical energy that was stored in the molecules. Okay, so here we're talking about the chemical energy. And so if the substances involved in the reaction are the system, then the released energy causes the temperature of the system to increase. So energy in the form of heat is transferred from the hot system to the cooler surroundings. Well, this leads us to the first law of thermodynamics, which you've probably heard of. Basically says that energy can neither be created nor destroyed. I like to think of it as what comes in must come out. So basically, if we take in 5 units of energy, 5 units of energy must be either stored or come out. So in order for us to really analyze the energy changes that we're wanting to understand in different chemical systems, we look at what's defined as the internal energy. And so internal energy is just the sum of all kinetic and potential energies of all components of the system. So we call it capital E. All right. So by definition, the change in internal energy, which when we're talking about the change in internal energy, we're talking about delta E, okay, shown here. It's just the final energy of the system, E final minus E initial. Okay. And if we look at this figure over here on the left, the internal energy includes not only the motion and interactions of hydrogen and oxygen molecules, okay, but it also the nuclei and electrons which are bumping together as well. Okay. Anytime we talk about delta E, you need to realize it has 3 parts. It has a number, whatever that value is. It has a unit, okay, joules, kilojoules, whatever it is, and a sign, either positive or negative. Well, if this change in internal energy is less than 0, which means the E final is less than E initial, then the system is releasing energy to the surroundings. Okay, so it's releasing energy to the surroundings. This energy change is called exergonic. Okay, if this delta E is positive, which means E final is greater than E initial, the system then absorbs energy from the surroundings, so it's taking it from the surroundings, and this energy change is called endergonic. Alright, so when we're talking about internal energy, and we're talking about energy in general, we know that energy is exchanged as either work or heat between the system and the surroundings. Okay, so the easiest way to think of this internal energy is really by thinking of it as a bank account. Okay, so here's our bank account. If we make a deposit, okay, we're increasing the amount of internal energy in the system. Okay, and a deposit just means that basically we're adding heat or there's work done on the system. Okay, so this means that we can describe delta E as just equal to Q plus W. All right, so if heat is added to the system or work is done on the system, the internal energy increases, whereas if heat is lost or work is done by the system, then we start to lose internal energy. Okay, and so here we can really define the different sign conventions for either heat designated as Q, work designated as W, and delta E as well. Okay. All right, the last few slides we're going to look at to really complete this lecture. Basically, we said that energy is the capacity to transfer heat. So we have words to define that heat transfer. Okay, if heat is absorbed by the system from the surroundings, we call that an endothermic reaction. Okay, if heat is released, like when something explodes and you have fireworks and so forth, heat is released by the system into the surroundings. We call that exothermic. Okay, so you should know those terms. So usually we don't really have a way of knowing the internal energy of a system, right? When we find that value that, or trying to find that value is just very complex, a very complex problem, okay? But we do know that the internal energy of a system is independent of the path that it achieved that state. Let me give you a brief example of this, what really helps drive this home, and we're going to define what a state function is. If I gave you a bucket of water at room temperature, came in, set it down in front of you, it's at room temperature, and I asked you, how did the temperature get to room temperature for this water bath? Some people might say, well, it was a boiling pot of water, you allowed it to cool, okay, and reach room temperature. Others may say, well, you must have had a bucket of ice, it melted and reached room temperature. Okay. Well, this tells us that internal energy is a state function because it depends only on the present state of the system and not the path it took to get there. Okay? So the change in energy is only concerned with the initial and final energy. Okay? So when we define a state function, it doesn't really matter on the path it took to get there. It's just this is the value. Okay? So when we go back to this, basically in the system, the water could have reached room temperature from either direction, right? We don't really know the path by which it achieved that, but we know that it reached room temperature. So internal energy is a state function. However, Q and W, the heat and work, are not state functions. Okay. Basically here you have a figure that shows a battery can be attached to either a fan or to this heating coil. Okay. And we're going to drain that battery from charged battery to discharged battery. Okay. If it's in that heating coil, part of that, or all of the energy from that battery is discharged as heat. However, for the fan, it takes work in order to turn the blade, plus it takes some heat to discharge that battery. Okay, so the internal energy, which was lost by the battery, is a state function because it doesn't matter how we got there. But you can see that the heat and the work are different when it's connected to two different systems. Oops. So that concludes part 1. We'll pick up with enthalpy in part 2. One thing I would encourage you is this is a very complex chapter. In order for me not to give you a 1-hour lecture for each of these videos, I've been brief, so make sure you go through it and read the book. This will help drive home some of these points, as well as emailing me if you have any questions. And you should probably look at some of the practice problems and the worksheets and the homework in order to understand how you need to apply these as well.